Okay. Welcome back. Everybody made it. You didn't panic too hard. Everybody did come back. That's good. It's normal to be a little fuzzy, a little overwhelmed a little bit. What in the heck did I get myself into at this point? And I'm hearing that loud and clear on the discussion board and seeing it in your faces. And don't worry, we'll get there. And Alex, I love your kitty. I wish I had mine here. Okay, so first off, the discussion board looks really great. I've had a couple people even turned in their journal articles. Anyone having difficulty finding journal articles? Nobody wants to say. Maybe you haven't looked yet. Let me know if you are and I can help you out. So on Canvas, discussions. So the discussion board that's today, this was due at today at 4. I think everybody did it, so everyone got credit. I was catching up on that before class. This next discussion board is due on the 22nd, which I believe is Tuesday. And this is commenting about the articles that you're finding or not finding in your field and what you're seeing there kind of in general. And then the next one that's due a week from today is on the new reading and videos for you to start watching and reading over the weekend and into next week to prepare for next week. So today, you were supposed to have read chapter 2, and we went over the formulas and kind of the theory, fuzzy stuff Tuesday. Today, we're going to do more of a looking at examples, more labby type feeling today. Next week, we're going to hit chapter 3 in Hawks. So your new reading is the Hawks chapter 3. It's a tiny bit longer, but it is based on an example most of the way, I believe. And just hold on to those equations. There's 28 minutes to watch on another one of those HLM videos in that series. I know I'm kind of jumping around in it. You're welcome to watch them in whatever order. And you can watch more than I'm saying, but first 28 minutes here goes along really good with the Hawks' chapter 3. And then it's optional, but I really, really highly suggest if you have enough time, at least watch the first half hour, 45 minutes of this video. I know it's long, it's an hour and 45 minutes, but it is one of the best talks that I've seen recorded about multi-level modeling. So this guy is phenomenal, John Neslick. He's very well known. He's very, very, very well published. He's a bigwig, and he does a really good job, I feel like. I mean, he is kind of a little pompous, but a good job of kind of giving you a big picture idea of multi-level modeling. And this is something he does day in and day out. And he was earlier to adopt this back in the early 90s. So he has a lot of context with it. Are you eating popcorn?
That was me last class.
Huh?
I did that last class.
Like, we can't go to the movies. Let's at least, make class. Yeah. So Neslick, he talks a lot about the multi-level philosophy, and he has some really simple boiled down examples about how if you have multi-level data, but you analyze it with a single level model, you get the wrong results. And they're very impactful, I feel. So the first 45 minutes are a good overview, and then I put some kind of bullets of some kind of after about the 40-minute mark, some main things that he covers if you need to go back. The ICC issue, so Joe, with your article, this would be a good one to look at. He doesn't explain it fully, but he brings up the issues with ICCs. He talks about power and sample size. It's a big deal with multi-level. And slopes as outcomes. This is a really good way to think of multi-level model. And this is the Radenbush and Brooks kind of philosophy as well. At the 119 mark, he starts talking longitudinal models, and we're not going to do that for a while. It would be good to hold off and not watch that yet. We're just doing cross-sectional cluster data for a week or two before we flip and do longitudinal. If we do both at the same time, it gets really confusing. He talks about, for 4 minutes here, why you should use MLM. And I know some of you do a little bit with partner or dyadic data. He talks a little bit there, and it might interest some of you. But no pressure to watch the whole thing, although I think you should. But this video and this chapter go really well together. So again, just basically the same thing. Summarize what you've learned. What questions does this bring up? This chapter 3 talks about estimation techniques, and we'll talk about that more next week. There's Bayesian, but we're going to focus on maximum likelihood and restricted maximum likelihood. And then, did something in the reading your video help things click for you? I notice when you guys, something works for you and you explain it, it helps someone else in the class more than if I just say the same words. So thank you for helping each other. This is how research happens, not in a vacuum, but it's everyone coming together to collaborate. And I really think that that's going to strengthen what you learn here. And if something's still fuzzy, put it down and I can make sure I hit that in class, or I'll send you a link for other people that are interested in that and still wondering about anything, because I'm sure there's going to be questions after it. There always are. Okay, so that's the next kind of like stuff to do. Tomorrow I will be posting the next homework assignment. I got to tinker with it from last year. But you can hold off to Monday or Tuesday to start it. Get those journal articles found and assignment homework 2 done first. Okay. All right. Okay, I'm going to go to the encyclopedia, to the volume 5 on multi-level analysis. And this is where most of the examples we're going to do in class are going to live here. And I have a lot that I put up here other years, and I'm going to try to expand and add to. So this is this I see being a free open source forever. And I have a lot of students that come back to this in the future. So this can be an additional reference. It's nothing new. I'm taking examples out of textbooks, all different kinds of textbooks and manuals, and doing them in R, so it gives you software to reference, and their examples as well. So we went over a lot of formulas last time, and Hawks is fairly consistent with his notation, the letters he uses, the indexes, the numbering, but that's not always the case. Some of you expressed frustration because even on some of the videos, even though I love them, they are using different letters. Did anyone notice that? I have all these textbooks. Every textbook uses a slightly different notation, and it is crazy. And that has happened because it's not just statisticians that have developed these models. Statistics is a very unique field because very few people study statistics to learn more about statistics. Usually people study statistics to learn something about something else. And so methods are often being developed and worked on independently in lots of different fields. And the different fields have a slightly different focus and vocabulary. And because of that, everyone comes up with a slightly different nomenclature, and it's hard to compare the equations straight across. Because of that, I made the first chapter in the encyclopedia, I'm calling the Formula Warehouse. So I'm warehousing the formulas that we use. So if you ever need to refer back, they're in one place. So little n's are for smaller micro units, and capital N is for the number of macro or groups or clusters. That's usually the notation we use, the distinction for multi-level. I is for the micro units, we're talking pupils, and J is for the clusters. And so I have kind of outlined all the regression equations that we went over last time and that we will through the class. So this is a good place to come back, a touchstone to look at these in the future. Okay, so Joe, when your article, it was talking about ICC. So here's formulas for ICCs for 2 levels and 3 levels. And then, oh, and there are typos. I'm seeing these as I'm going by. Yeah. Nobody's editing for me. And maybe someday. And then proportion of variance explained. And those were the 2 concepts I think they were confusing, because they can be confusing. And so here's maybe that can help you sort that out. Okay. But enough about notation. Just wanted to hit that. We want to do the student extroversion popularity example. Does anyone have any questions about the chapter or the example before we get in? I need to rest my voice for a second.
Will we be able to follow along in R for this?
Yes and no. So okay. In our files on Canvas, I have a folder for lectures, and in there we're on lecture 2, Intro to MLM 2 levels, 2 level models. There is a skeleton, or I think it's right here. There's an R markdown and kind of a knitted PDF. That was an outline, and in past years I've had everyone follow along in R, but it ends up taking too much time. So I'll probably scroll most of it for the sake of time today, and then next we'll do it live coding. Okay. Great question. How was it to follow along Hawks's example in chapter 2? Could you follow it? Was it all over the place?
I thought it was fine until the end when there was so many moving parts in the equations, and then it got hard to follow.
Okay. All right, with that in mind, I think I want to start with the end in mind. That's like one of the 7 habits of highly effective people that they teach to the kids in the elementary school. Start with the end in mind. So I'm going to come all the way down to the bottom of this page and put your mind at ease. Yeah, there's a lot of, I have all the code you would need to do all of this and all the output all in here, mostly so I can reference it. Because if I don't do this for a month or 2 and I get a new project, I'm always, what was that again? And I was always hunting on my computer and folders, trying to find old code. Now I can find it. Okay, so before I look at the plot, here is a table of a very complex, well, kind of complex, multi-level model. This has, we're predicting student popularity from the students, whether they're a boy or a girl, how extroverted the teacher rated them, how many years the teacher has taught, and an interaction between extroversion and teacher experience. This top of this table, what does this look like? I think it's because you have the two computers. I think it, yeah, this looks like a linear model, the LM model, just like we did last week, right? For each predictor, we have an estimate with a standard error and some stars. And I made this by using TechReg. I had us do it last week on purpose to prepare for this. So you can make a TechReg. This one, it's a website, so I'm using HTMLreg. But if you're on screen, you would use ScreenReg. If you're wanting to make a PDF, you could use TechReg. But it's the same thing. You put your model in, you can add some options, and you get this table. The top part of the table is exactly, for multi-level, is just like for regular multiple regression that you've learned before. And the interpretation is the same. And what do we do when we have an interaction? Is this number estimate obvious? No. So we make a plot. So there's more stuff on the bottom. We're going to talk about that later. But the top part, that is usually the part we care about is the top part. Same interpretation as regular regression that you already learned. So here I've made a plot. Okay, let's look at this plot. Make it bigger. Okay, so I have a panel for boys and a panel for girls. What do you notice about those two panels?
Slopes are the same, but intercepts are a little different.
They look exactly the same, except for the girls is a little bit higher, maybe just shifted straight up. And that's because in our model, let's scroll back up, girl sex is only a main effect. It's not in an interaction. So the estimate 1.24 tells me that the girls are 1.4 points higher than the boys. Other than that, it's all the same. So do we need both panels? It's kind of redundant. So a rule of thumb with plots is if it's redundant, remove it, because it can be confusing. Because people are going to be going back and forth. If it's identical, don't bother. Okay, so here is just one plot. This is for the boys, I think. No, yeah, because boys are the reference category. So here's the boys. So what do we notice? What's the relationship? In general, what's the same about all those lines?
Positive slope.
They're all positive slope. Thanks, Mike. Since they're all going up, that tells us what's the x-axis? That's how extroverted the kids are. And what are we predicting? Their popularity. So the more extroverted a kid is, the more popular they are. And the more introverted and shy, quiet, the less popular they are. In general, that's true across the board for all the lines. But there are different lines because that relationship depends on teacher's experience. So the teacher's experience moderates the relationship between extroversion and popularity. But the idea is we knew that they moderated each other because the interaction got 3 stars. So it's significant, but to know in which way, we need a picture. So if we look at the picture again, let's compare. Now, gender were categories, but extroversion is a continuous variable and teacher's experience is continuous. But we can plot it if we choose some values for teacher's experience. So I've chosen 5, 15, and 25 because they are evenly distributed in the range that the data have. So let's look at the dotted line at the bottom. These are new teachers. They've only taught for a few years. What do you notice about that slope for the new teachers?
It's steeper than the other ones.
It's really steep. So there is a strong, very much correlated relationship. We can see that extroverted, very popular. Introverted, unpopular. That's a very steep line. What about the battle axe teachers that have been around forever? These solid line. It's almost flat. So for all extroversions, they're all about the same popularity. It's a little slant, but not much. So those battle axe old time teachers, the extroversion is not affecting their peers' rating of popularity. Could you interpret that without ever hearing what a multi-level model is? The picture makes this accessible. You don't have to understand those equations to be able to understand what the model's telling you. That's the good news. It's helpful to know what you should put in to the model to start with. But after you get your model, it's understandable if you can know what betas mean in regression, and if you can make a plot, which we can do in R. Are you relieved? Okay, so that's where we're going. So let's go back to the beginning. Oh, come back. Okay. So here's my little picture I put together, because visual learner that I am. So to review, in this situation, this is made up data. It's made up so that it will behave nicely, because real data can be finicky. So they built this data set based on real data. This is nice data because we have exactly 100 classes. Each class is a different school, and each class has exactly 20 students. How likely are you to get that data in real life? In real life, one's gonna have, class is gonna have 10 because they gotta also get parent informed consent, and one's gonna have 12, and one's gonna have 3. But nice data. So we have 100 classes of 20 each for a total of 2,000 students. So this picture is showing that even though we have 2,000 students, is that our only sample? We have a sample of students, but we also have a sample of classes. This is how we figure out the structure. So Nesdeck, I probably said that wrong. He says multi-level data needs a multi-level analysis. You know you have multi-level data because you have more than one set of samples. We have samples of students and samples of schools, or we have samples of students within our sample of schools. That's how we know we need a multi-level model. Not all data is multi-level, but this one is. So we need the outcome, the dependent variable, to be measured at the micro lower level. So the micro units are the different students, and we're gonna use their popularity, which is the average rating the kids in their class gave them. Now we have 3 predictors in this example.
Here's what I found.
We have the student's gender and the student's extroversion. Those 2 variables we want to know about. And so we want betas, for what we would have called betas that are now gammas. We want coefficients for those variables. But gender is the gender of a student. It doesn't make sense to have gender of a school, right? That one's clear. Extroversion also is something that is measured on students, or we could say extroversion pertains to students. So it's a student level predictor variable. Carly? Where's Carly? Carly raised her hand.
Sorry, I realized I didn't unmute myself. I started talking and I was like, what is she talking about? I just had a quick question about gammas real quick. Is that a cluster mean? You use that term in the homework and I wasn't sure if that was referring to gammas or not.
Can you hold that thought for 2 seconds?
Sure, yeah, sorry.
I just want to make sure that we understand the situation first.
Yes, of course. Okay.
Yes,
I'll
but that
give you
is
the question.
that is the new thing, right? We've
Right.
always had betas, but
Right.
now what's the gamma, right?
Okay.
Okay. That's like, it's like right down here.
Okay.
Thank you for bringing that. Okay. So teacher experience. Who does teachers experience in number of years taught? Who does that belong to? Who does that pertain to? Who was that measured on? Teacher's experience.
The school or class level.
It belongs to the whole class. We can ignore that and pretend like it's regular regression. But this orange class, they all have the same teacher. And if their teacher's taught 10 years, Johnny's teacher has a teacher with 10 years, Sally has a teacher with 10 years, everyone is going to have a value of 10. If we pretend or bury our head in the sand and pretend like we disaggregate, we give that value to all the kids, the class is the same. It's homogeneous. That's what shrinks our standard error and makes our p-values too small and inflates our type 1 error. That's what makes non-reproducible results. And who wants to publish something that nobody else can reproduce? No.
Except
Sorry, wrong computer. Except I just had a quick something that just came to mind. I thought I was understanding this. Then why don't they just turn something like teacher's experience into another predictor variable rather than turning it into this level 2 idea? Because it seems with everything else, I mean, gender you could think of gender almost as a different level too. I mean, everybody under level girl or boy. You know, why don't they turn schools even to just school 1, 2, 3, 4, 5 and have it as another predictor rather than like a whole level?
This is key. This is so key. Thank you, Joe. We talk about categorical variables as having levels, right? So gender has the level of male and level of female. And diagnosis might have levels of autism and ADHD, etc. Those levels of a categorical variable are not the same as a level in a multi-level analysis. Same word, different meaning. Here's what I go by. A level is a sample? A level in a multi-level analysis is a sample. We have a sample of students on which we have measured gender and extroversion who belong to a sample of schools on which we have, or classes that we've measured the teacher's experience. You are right, Joe, that teacher's experience will be a predictor variable, just like gender and extroversion. It will be a predictor, but it pertains not to the student, but to the class as a whole. I'm seeing some nods. Are there some no's? Is teacher's experience a sample? Well, we've got some values, but the sample is the classrooms or the teachers themselves, not something we measured on them. A measurement is never a level. A level is made up of, is a sample that has selected units. And sometimes it's not clear. To do this, you really have to think about and be involved in and know the intricacies of how the data was collected. And the only thing that's really going to help is more examples. That's why this is not a 1-hour workshop. I get asked to give a 1-hour workshop on multi-level models every year. What do you think? Could you learn what we've learned so far in 1 hour? And we're just starting. Okay, so here's our scenario. Okay, so there's the clarification. Levels are made up of a sample of units. Our level 1 is made of the micro units that are called students. Our level 2 is made up of the sample of the macro units of classes that are clusters of students. On the micro units, we have measured the outcome, popularity, the gender predictor, and the extroversion predictor. On the classes as a whole, the macro units, we've measured the teacher's experience. So in this scenario, we have 3 predictors, 2 at level 1 and 1 at level 2. You can have predictors at level 1 only, level 2 only, or both. It depends. Okay. So here's our data set. Now let's come down here. So yeah, let's look at the data for a second. So we have 1 line per observation. So we have 1 line per pupil. So we have per kid 1 in class 1. And there's their extroversion score, whether they're a girl or a boy, the teacher's experience. So this first class, notice everyone in class 1, their teacher is taught how long? 24 years. Are the students independent? No, they share the same teacher with 24 years of experience. If I scroll down far enough, eventually I get to class 2. In class 2, their teacher has 14 years of experience. They share that same teacher. And then we've got their popularity, and we're not going to worry about this other variable. Okay. So we can make summary statistics. Here's table 1. We saw furniture table 1 before. Here's some example code. So, you know, boys and girls, are they the same? The answer is No, they're not the same. Okay, so visualization. I preach visualization and summary statistics. Together, summary statistics and visualization are called exploratory data analysis, and it's often overlooked. The more complex your model, the more you need to understand before you do the model. What's the quote in the book? Some statistical software does not a statistician make. So have you heard if you put monkeys in a room with typewriters long enough, they'll write a novel? This is one side effect of computer software, is lots of people can run models. But is that good enough just to run models? You need to know which model to run and what it means after, right? And you have to be able to tell someone else. That's the third thing. You have no hope of understanding a complex model if you don't know your data first. Know your variables 1 at a time and 2 at a time and so on. So here is my first attempt to get to know this data. I did a scatter plot. I have extroversion, one of our predictors, on the x-axis, and popularity, the outcome dependent variable on the y-axis. What do you notice about those points? There's several things I can pick up. What do you pick up?
As far as distribution along the extroversion scale, it actually looks pretty evenly distributed. As far as the most people, about 5, and then normally outwards from that.
Most people are in the middle and then they're out from that. Yep, on extroversion, it's fairly normally distributed. It's one thing, yep. Let's have 2 more. Carter, you're unmuted. What?
I'm trying to think if this is even worthy of mentioning, but something I just noticed is like all the values are on whole numbers, which isn't always the case. I guess I'm used to where you have a lot of means, and so it looks more like that kind of cloud shape. So they're just, yeah, they're all clustered on whole numbers.
Yep, and that's because, and you need to know these details about the data you're going to work with. The extroversion, they asked the teacher to rate the student on a scale of 1 to 10. So they only gave a whole number, and that's why you see the strips in your points. Is that extroversion really continuous? Not really, because it's only whole numbers, but when you have that many numbers, 10 numbers, some people say 6, some people say 8, but 10, and they're spread mostly in the middle, fairly normally distributed, like Joe said, you can usually treat it as if it had been continuous. Yeah, what about popularity? Do we see that with popularity?
You mean normally distributed?
Or continuous on the full spectrum, or just whole numbers?
It's continuous, and it also looks fairly normally distributed.
Yep, it looks fairly normal. It is continuous. For the popularity in each class, all the kids had to rate each other on how popular they were. And so it was the average. So the average, even though they rated them from 1 to 10, the average gets to be a decimal number. Okay. What about the association or correlation between extroversion and popularity?
Moderately positive.
Moderately positive. Yeah. So I've added that regression line. Okay. Now this is kind of a hard plot because Carter pointed out we have those strips for only whole numbers. There's a lot of over plotting. So it's kind of hard to tell because there's so much ink. So this is for just your own information. There are other ways to plot it. Here's one way, and the code's here if you're interested. Here I've grayed out the points and I've added contours to kind of see the cloudness a little better. Does it look football-ish shaped? Yeah. And this is another one. It's a hexagon plot. This works better if they're not only whole numbers, but there are other ways to plot things, just to show you. Okay, so here's another way. Because it is stripped, we could do box plots side by side. And you can still see that positive trend. The higher extroversion on the x-axis, the higher the popularity on y. Okay. So if we do regression, do you think extroversion, and we already saw the end, so hint, you know, does extroversion affect popularity? Yes, that two-way relationship seems to exist. Okay, thanks for nodding. Okay, so what about clustering? So this is everyone all mushed together. But the question is, does it depend on cluster? Are the clusters more or less the same, or are they significantly different? So I did the scatter plots one class at a time. Here's the first 9 classes. What do you notice? Is the regression line identical in every class? Megan's shaking her head no. Yeah, they're not. How do they differ? What's different about some of those? Megan, you shook your head, so what's different? Your mic's not picking up. Someone else will have to jump in. Someone save Megan.
Well, probably the mean and the mode, right? Like they're just clustered in different parts of the scale.
Yeah. How many points are on each panel? Each class has only 20. And so that regression line is can be a little flexible because it's only 20. But on some, you're right, Carter, some are different up and down on the mean, some are different on the slope, steep or flat, because they're a different set of 20. Now here's the first 9, but I picked out some more variability. Here's another 9 that I hand-picked. See this class up here in the upper right-hand corner compared to the class down here in the bottom left? There's a lot of class-to-class variability in addition to student-to-student variability. These are the U's. The U's are the class-to-class variabilities. The E's are the student-to-student variability within a class. So no points are exactly on the line, and every line is just a little bit different. I had someone who did an analysis here on campus, and they were a clinician with audiology, with cochlear implants. And they had gathered data, and they had had a master's student analyze the data. And you can imagine what the master's student's statistical sophistication was. Maybe had 6,600, maybe had some regression. They had something like 300 people, and it was longitudinal, but they fit a line for each person. So it would be like this. Each of those red lines are a regression line. and each regression line has a slightly different slope. And then they had taken the slope of each line and made a distributional plot. It was good thinking, but when they submitted the article for review, reviewers said, use a multi-level model, at which point they came to me because they didn't know how. And that's the idea behind multi-level models. We could do a regression line for each class and then analyze the slopes in a second stage. Sometimes multi-level models are called a two-stage analysis. First, you study the clusters, the units in the clusters, and then you study comparing the clusters to each other. We take the slopes from the individual analysis to make a second analysis. In that video, the one that I said was optional, but you should watch, he calls it slopes as outcomes. And that's the Rodenbush and Brooks philosophy, which is what we're going to do, plus some shrinkage. That's the main idea. All right. Questions before we move on? So quiet. Okay. So all these red lines are regression lines, one for every class. What if I got rid of the points and I threw all those red lines on the same plot? That's what I've done there. Are they all the same? Now we can look at all 200 classes at once. Are all the slopes identical? Are all the intercepts identical? No. But are the slopes telling us something? Is there an overall trend with the slopes? Some are flatter, some are steeper, but in general, they're positive. Is it better to have one class or 200 classes? More is better with a sample. Could we study teacher experience if we had one class? To be able to look at the role of teachers' experience, could we have 3 classes? Probably not. We need a good number of classes as well as a good number of students per class. And however, how many is enough? Watch the video. We'll talk about it more. It's a later chapter in the book, but depends. There's the answer. Depends. Okay. So this is sometimes called a spaghetti plot, because it looks like I took a package of spaghetti pasta, ripped off the package, and threw it on the table, right? Sometimes I call it a hairball. So we can see some general trends, but what's the role of teacher experience? What's the role of gender? We don't know. So what we're going to do is tease apart this hairball by separating into panels. Let's separate boys and girls, boys on one side, girls on one side, and let's separate low, medium, and high teacher experience. And I do that with the facet grid to make panels. So here we go. So yes, we see positive slope, but is there any other trends? Let's see boy versus girls. What trend do you see boys versus girls?
The intercepts are a bit higher for girl.
If you look at the pink lines versus the blue lines, in general, the pink lines are higher. So the intercepts or the means are a little bit higher for girls than boys. Oh, the odds favor the Packards. Sometimes. Anyway, so when we separate this out, we're doing exploratory data analysis, but we have an idea that our model should include a main effect for girl versus boy. Does it look like the slopes are different for boys and girls? It's hard to tell, but probably not. What term would we put in our model to look at if the slopes were different by sex? I'll wait till someone comes up with an option. Does extroversion's role depend on sex?
It doesn't really look,
Interaction.
Julie, what were you gonna say?
so it doesn't really look like it.
It doesn't look like it, but what term would it be? You're right, it doesn't look significant. Mike, did you answer too? There were a couple mics at once.
Interaction is the word you're looking for.
An interaction. And if the slopes were different for boys and girls, it would be an interaction between sex and what other variable?
Extroversion.
Extroversion, because that's the slope pertaining to the x-axis of extroversion. Okay, now that's the colors, blue versus pink. Now look at the rows. On the bottom, we have the less than 18 years or more than 18 years, the long time teachers. In the middle are the medium experienced teacher. And at the top, we have the not very long teaching. Is there a difference there? Can someone describe a pattern you see as you move from less to more experience with the means or the slopes? Ariel?
So the slopes are more positive for girls less than 10 years old.
Yeah, these lines up here are the steepest. And as we come down here, these lines are the flattest. On boys, it might be a little harder to see, but do we see the same thing for boys? Up here, the top blue lines, they're the steepest, and as we come down, they become flatter. It's hard to know for sure, but it gives us an inkling there might be an interaction between what two variables?
It's a cross-level interaction between the teacher experience and the extroversion.
That would be the teacher's experience and extroversion. And we call it a cross-level interaction because extroversion pertains to the students, the micro units, and the year's teaching belongs to the teachers or the class, the macro units. So that's why we call it a cross-level interaction. Is this better without equations, with real data? Well, real. Okay, so this is again a spaghetti plot, and this has been stratified or separated by the other predictors because you can only have one predictor on the x-axis. So to involve other predictors, you can do panels or colors or both. Okay. So single level regression. Let's look at here would be a single level regression with main effects at level 1 only. So if we didn't have clusters of classes, we could say, does the popularity of I student in J class depend on an intercept, the effect of their gender, and an effect of their extroversion, and then we have our residuals, the student-to-student residuals. That's old hat, simple linear regression. But are the intercepts and the slopes for every class? We saw that they are in fact not, and they depend on teacher experience and gender and all the covariates. So in single level regression, and this is, let's see, who was it? Carly, you asked about the gammas. So here's where it's coming in. It was a little longer than I thought. I'm sorry, I promised we'd get there. The betas are the coefficient or role of predictors when you have a single level. Gammas are the grand intercept and the grand slope averaged across groups. So we have a beta for, or a slope for each class, and if you average them all, that gives you the gammas. The gammas are the average of all the betas.
So would it only be a clustered mean if it's a categorical predictor?
We're going to see some examples that are not categorical.
Okay.
Okay. Okay. All right. So this was what we did before. We would say LM, here's the code, and then we'd give the formula that popularity, our dependent variable, is predicted by the little tilde, and then we would put the names of our predictor variables with the plus to make main effects. How would we change that to be an interaction in the code?
Asterisk.
The plus would become an asterisk, and that would mean to include the interaction. Thanks, Candace. And then we have to tell it which data set to do the model to, because you can have lots of data sets in R at the same time. And then the summary gives you the summary. And the first part of the summary are the coefficients. Does it say beta? No. What does it call betas? What word does it use on here?
Estimate.
Estimate. They're the coefficient estimates. And then they have a standard error. And if we take the estimate divided by the standard error, that makes a t-value. With the degrees of freedom, they combine to make a p-value. This t-value that gives us the p-values with the flashy stars, that's called a Wald test. W-A-L-D, because he's the guy that published it. We are going to see these in multi-level. That's why I'm pointing it out. Okay. We also see some stuff about the residuals. It also tells us what the call was, how we made this model when we do the summary. Okay. So we have betas. Our beta naught is our intercept, and then we have our slopes. So which are the effects of our two main effects of our two predictors. I'm kind of skipping some of this. Now, before this model had two predictors in it, right? We can fit a model with no predictors. Why? Let's see. This is called a null model. Null means no. It has no predictors. The null model will always have an R squared of 0. It will never predict variance, because all variance will be a residual variance. The only thing we have in this model besides residual variance is the intercept. When you have no predictors, the intercept is the grand average. So the null model tells us the grand average. So that does something. Null models are helpful because then you can fit a model with predictors and see if it fits better. This is important. Chapter 3 goes into it more next week. But you remember those Wald test statistics with the p-values and stars here? Remember these things? They are not trustworthy always in multi-level modeling. You cannot rely on them. Because how do we make this t-value? We take the estimate and divide it by its standard error. It's assuming that that follows a t distribution, a normal distribution. And that is not guaranteed to happen if you have clustered data. It's only true if you have single level data. So we need another way to see if variables are significant, since we can't rely on the Wald test. And we're going to do that by comparing nested models, models that become more complex, and seeing if they fit better. So that's why a null model can be helpful, because we fit a null model with nothing, and we fit a model with something and see if it fits better. If it fits better, the predictor must be important. That's called, well, we'll get to it. That'll be next week, but just bringing that up because some students don't connect why we don't just use these p-values. It's different. There are differences. Interpretation, much the same. Finding significant, a little different. Okay. All right, so one way to compare nested models is by fit. Now, this is a little confusing to me even, why they use this word. But in R, to compare nested models, we use the word ANOVA. We're not doing an analysis of variance like you learned in 6600. They're recycling because the math is much the same, but it's not the same thing. When we say the word ANOVA, and then in parentheses give it multiple models, it compares how the models fit compared to each other. And this is one way you can see if variables are significant. This gives you an F test with regular regression. We're going to do something very similar for the multi-level models, so there's not totally foreign. Okay. So here's my little light bulb moment. The intercept only null model is useful because it serves as a benchmark to compare other models to. Even though it doesn't tell us anything more than the grand average, it is our benchmark to build our model up from. So here's our friends, the equations. So this first equation is a regular regression model with no predictors if we only had one level, if we only had one sample. What's the beta 0, the beta naught? What's that mean in regular regression? Beta 0 is, someone said it.
The intercept?
The intercept, thank you. Is the intercept the same for every cluster? No. The intercept for a cluster can be averaged. The gamma is the average of all the clusters, and each cluster is a little bit plus or minus onto that grand average. So the gamma is the average beta for every, putting all the groups together. Does that help? Carly, you were the one that was asking about these gammas. So if the beta naughts are intercepts, the gamma naught is the average of all the intercepts.
Got it.
Sweet. Okay. So we have the betas are the gammas plus or minus the U. The U is the disturbance, how much it's off by, because each group we know is a little bit off. The U is how much it varies. The groups vary around the grand average, in this case, intercept mean. Now we've done algebra, right? We've all done algebra. We can substitute equations. So this bottom equation, the level 2 equation, beta naught is equal to gamma plus U. So gamma plus U, that can go into the top equation in place of beta naught. So when we make that substitution, we come up with not 2 different equations, but one combined equation. And where's the beta? It got substituted with the gamma and the U's. So instead of having betas, we have gammas and U's in addition to E's. Ugh. So the gamma naught, and it says not, it's the way they do it, I'm sorry, is the average intercept of all the groups. The U0 is how much each group randomly varies around the grand average, and the E's are how much the students average within their group. These numbers out here, these are the equation numbers that are in your Hawks book. Unless I made a mistake, I tried to line them all up. Okay, should we add some predictors? Oh, let's fit this model first. This is a null model. Why is it a null model?
Because there's no predictors.
No predictors. So how do we put that in? Well, let's go back up here to the LM model with null model. I don't think we looked at this before. Okay, so we talked about a null model with simple regression. Here's the syntax. We have an outcome, popularity is predicted by, we don't have any predictors. You can't leave it blank. So instead of leaving it blank, we put the number 1, because if you times anything by 1, what happens? Stays the same. So if you take beta times, because usually the beta, it's beta times an x variable, but there is no x, so it's beta times 1. So the 1 represents the intercept. So this is how we do a null model, and we use LM for a linear simple regression. We're timed to do the first code for the first multi-level model. I'll come down here. And you are going to be surprised at how similar it's going to look. Okay, here it is. Okay. We are going to use a package called Lemur Test. That's how I say it. LMER stands for Linear Mixed Effects Regression. Mixed because we have fixed and random. Linear because the betas times the predictors added up is the linear. Lemur Test. The original code is packaged in, let's see, a package called LME4 by a really great guy named Bates. But if you use his package, it will never give you a walled test. And I already hinted, walled significant tests cannot always be trusted in multi-level models. And so much so, he is adamant you should never look at them. So his package never spits them out. But there's other people argue, well, you can't always trust them, but sometimes they're a good guide. So I want to look at them. So the Lemur Test package is kind of a wrapper that does the LME4 and adds walled tests to it. So LMER test is our package. The function is LMER. Okay. The first thing we give it is a formula. Look how similar it is. The name of the outcome, the dependent variable. Then we have our tilde wave, and then we have the number 1 because we're doing a null model. That much is the same, right? Let's hold off on the rest of that line, ignore it for a second. Then we have to tell it which data set. And then we have this new part. REML equals true. And I'm going to hold off on that. Chapter 3 that you're going to read next in your book talks about that. REML means restricted maximum likelihood. That's next week's discussion. It's just another option we didn't have in single level regression. You can either make it true or false. Next week we'll talk about it. But let's look back at this formula. So we start the formula the same. This is a new part. Okay. So the formula at the beginning is fixed. Everything we want a coefficient for. Everything that's in the parentheses is random. Now we're fitting a null model, so we're going to have a fixed intercept and a random intercept. Those are our two pieces. So we have a 1 out in front to say we want a fixed intercept, And we say a 1 in the parentheses because we want a random intercept. The intercepts or the means are going to be average because they're going to be different for each
level.
What are the units of the level? Or we're going to have a different average intercept for every
Class.
Yes. So we're going to have that vertical bar, you can think of it as for every. So we're going to have one fixed gamma intercept plus a random intercept U for every class.
So why does the one first mean fixed and then next mean random? Why does
Outside of the parentheses means fixed. Inside of the parentheses means random. We never had the random part before. This is the new part, is adding that random part. So it's outside the parentheses is fixed. Inside is random.
is it 2 outside of the parentheses random? Can
We
you have,
never use a 2, we just use 1.
what if you put a 0 where the 1 is in front of that line?
If you put a 0 there, it would mean no gamma, which we almost never want to do. And we can discuss why at another time. Okay? Because we have 18 minutes. I don't want to leave you hanging. Okay. How are you feeling about this code? Is it totally foreign? There's new stuff, but not really. So those of you that are new to R, this is the good news. Everything you learned before gets recycled. Some people go, oh man, I'll never learn it all. But we keep recycling the same things. So that's good, okay? So just like LM models, we can do summary of the name that we've assigned our model to. So I assigned, arrow, this model to the name Pop Lemur 0 Re. I could call it Bob, but this is to remind me, this is for popularity. I fit a linear mixed effect regression model. The 0 reminds me it's the null model. And RE reminds me that it's, yes, it is restricted maximum likelihood. This is my own like jargon I've developed to help remind myself what these models are. You can name it Bob if you want. You can name it Fit1 if you want. It doesn't matter. But if you do summary, let's look at what the output looks like. Okay. It tells us what our formula was and what our data was, how we fit the model, if we've forgotten. It tells us we're using REML. Again, we'll talk about that next week. It gives us this thing about residuals. We saw that before. Oh, and look, we have 2 parts to the main output. We have random effects and we have fixed effects. Fixed and random make mixed. Okay, for a minute, let's just look at the fixed, because fixed is just like the betas, except for now we're going to call them gammas. But does the output say beta or gamma? What does it say?
Estimate.
Estimate. So this is our grand average intercept, which since that's all we have, it's the mean. 5. The grand average popularity of all students is 5. Remember that it went from 0 to 10, it averaged about 5. Okay. Now, they've done the estimate divided by the standard error to create a t-value, and they've gotten a p-value. What's this t-value, p-value thing called? What kind of a test?
Walled.
Walled test. Is this p-value trustworthy? Maybe not. But look at the size of this p-value. How big is that p-value?
Very
big? Is that what it means, Alejandro? Big? The big p-value? No, teeny. It's teeny. The e to the negative 16 tells us we'd have 15 zeros before we got to our first not zero number after the decimal. Teeny tiny. So even if it's not really reliable, even if it's off by a lot, it's still going to be significant. It's definitely less than 0.05 by a long shot. Okay, so that's how you interpret the fixed effects. You interpret them just like regular regression. Random, it doesn't give you estimates. There's no estimate there. What does it say instead?
Variance.
Instead, we have variance. We don't get the U's and we don't get the E's. We get the variance of the U's and the variance of the E's. This is why these are sometimes called variance components model. The way we read this, let me get my mouse over here, is class to class, the amount of class to class variance in the intercepts is 0.7. Now the units depend on what predictors and what outcomes you have. So you can't really interpret the units, but what you can do is compare it to if the class intercepts vary by an amount of 0.7, students within classes vary by 1.2. So you can compare class to class variation is 0.7, but student to student variation inside of a class is 1.2. Where is there more variance? Student to student or class to class?
Student.
There's more variation student to student than there is class as a whole to class as a whole. Sometimes it's the other way around. This is where we get the ICC number. Joe, it's for you. Okay, so here we go. Let's shrink this down. So this fitting the model, actually, I mean, deciding what to put in, we haven't addressed. But typing it, can you see where the pieces would go? And where the pieces get spit out of the output. Again, we don't know why you would do that yet or how you would choose, but this is how you would tell the computer to do it. And this is what the computer is going to spit back out at you. Okay, here's a little red note about estimation methods. I'm going to skip this because it's next week and we have 12 minutes now. So we're going to talk intraclass correlation. All right, couldn't be more timely for some people. So although the Null Model does not explain any variance, the R squared would basically be 0. What it does is it decomposes or divides up the variance into two pieces, person-to-person variance and group-to-group variance. And we can compare the size of those two pieces to each other. And that's the ICC. So we take the random intercept variance and divide it by the combined total variance. So mathematically, we would take the total variance, 0.7 and 1.2 adds up to be about 1.9. So we'd take class to class variance and divide it by the combined total, 1.9. And that gives us our ICC. When you have two levels, you only ever have one ICC. Question?
Yeah, is that residual, the person-to-person residual, is that measured or calculated person-to-person within a group, or is that the grand person-to-person?
Yeah, so this is a really good call. I'm glad Mike asked this question. Did we ever say anything in our model about kids, about their IDs? We didn't. So how do we know that residual means kid to kid?
Because it's the stuff that's not explained by the class to class?
One.
And the extroversion ratings are based off of individual kids.
Because think about our data set. Think way back up to our data set. How is our data set? We had one line per What, Julie? I saw you say it.
Per kid.
Per kid. So because our data set has one line per kid, the residuals are kid to kid variation because those are the smallest units. We don't have to say kid or ID of child or whatever we name that variable in our model because the model knows that's the smallest unit because there's one line per kid. We have to say class to tell it how to lump those kids together. Allison, question? No, I don't want to put you on.
I was thinking about my data set and how, yeah, anyway.
So Sarah, would the way you set up the model look different with the longitudinal data set? I'm wondering.
Yes, and I don't want to mix the two today. I want to hold off for another week. I know that some of you are just chomping at the bit to get to longitudinal, but I really want to hold off till, because longitudinal adds an extra layer of complexity. We got to get this.
Yeah, I was just thinking when you said like, because it knows because there's one kid per line, but if you have to change it if it's a long format, right? Okay.
Yeah, if you have a longitudinal data set, you have to make it so you have one line per time point.
Mm-hmm.
And we will get there, but that's the extra layer of complexity I'm talking about. Okay, so.
Did we get Michael's question answered?
Which was?
Is the residual variance 1.2, is that student to student variance within a class or is that overall?
It is always within class.
Okay.
Mm-hmm. Yeah, so the answer to Mike's question is yes. The residual variance is whatever you have one line per, and in this case, it's one line per kid. So the residual is kid to kid variation, and then it's always within class because that's what we put in our parentheses. So residual would be kid to kid variance, and class, residual is kid to kid variance within class. And again, that vertical line is within. You can think of the vertical line as saying the word within. If you have to type that vertical line, how do you get that on your keyboard? My sister-in-law asked me this in a text last week.
It's next to the brackets, to the right of it, at least on a Windows keyboard.
Braces above the enter key with the backslash. So that's the slash, not the backslash. Yeah, right above your enter key. Yeah. We don't always use that one. Okay, so there's the formula for ICC. There is a really nice function, and I think it's changed packages. I'm gonna need to fix this. I think the so this is a little bit of a growing pains with R. Sometimes packages change, and this SJStats package is just one guy. He's really smart, and he just puts stuff he uses a lot in there, and I use a lot of the same things, so I borrow them, but I think he changed it. But I will update this before we have to do it in the homework assignment. But you can say ICC of the model name, and it just plops out your ICC. So we said class to class variation was 0.7, and if we added the two together, we got 1.9. So look, if I do 0.7 divided by the combination of 0.7 plus 1.2, I did the calculation, it came out to be 0.36, but I just asked the ICC calculation for the model, and it plops out this number. So here's the interpretation, because this is something you don't get in single level regression. This is always a decimal number, and you can interpret it like a percentage. The ICC is based on the Null model with no predictors. It tells you the percent of variance in the outcome that is attributable to clustering. So in this example, 36%, almost 37% of the variance in popularity is due to class variation. These classes are very different from each other. Do we need a multi-level model? Yes. Now, on the, I want to point this out because we're wrapping up here in a couple minutes, so I want to make sure to point this out. This is one of the things, oh, not week 3. On the next, on that video, the long video, they said, please, you will want to try to watch as much as you have time for. One of the things he goes over, and it only lasts 6 minutes, so you can watch this part. He talks about the ICC issue. So, some people say, I will calculate the ICC, and if it's big enough, I need a multi-level model. But what if the ICC is small? Don't need a multi-level model. Does that seem rational? It's wrong. And this is why. And you can, he says it very eloquently. The ICC is always based on the null model that has no intercept, or no predictors. No predictors. It only has an intercept. What does the intercept tell you with no predictors?
Nothing?
The mean.
Mean, yeah.
The mean. It's a flat line, but it's at the mean. So the ICC only tells you about the percent of variance in the mean. Only tells you about the percent variation in group means. Are means what we're usually interested in about research questions? Mike's saying no. What do our research questions usually involve?
Kiddos.
Mean of kiddos? We just want to know the average of kids. No.
Kids individually.
And individually, yeah, but
We want to know trends.
trends.
Yeah.
We want to know about the effect of variables or slopes. Specifically, most of the time we want to know about interactions. Does this one thing depend on this other thing? The relationship. ICC does not tell you anything about relationships. Like I could have one group that the relationships like this, positive, and I could have another group that the relationships like this, negative. And what are the means? The means would be the same. So you can have an ICC of 0, meaning the group averages are the same, but have very different relationships in the groups. So this is kind of a fallacy that the ICC tells you if you need a multi-level model. If you only care about means, I guess so, but if you want to know about the role of variables, it's not enough. So people say if the ICC is at least 0.20, do a multi-level model, or if it's at least 0.16 or 0.73 or 0.17.295 based on some simulation. There is no cutoff. Okay, there's my soapbox.
Why do them all? Why do them at all then? Why do they even matter?
Because it's still an interesting bit of information. It is informative, but it's not enough to justify or argue against using a multi-level model if you're interested in relationships between variables.
And don't you need the ICC for your power analysis?
And you need an ICC for a power analysis. So please publish it for other people. How many of you guys are writing a proposal? How many of you are doing a lit review before your proposal? And how many of you are trying to find effect sizes so you can do a power analysis? How's that going for you? Do everyone a favor and publish effect sizes and ICCs so we can all do power analysis and do future research. That's another soapbox. Okay. So this red box is saying that I just said. Okay. Just in the last, oh, we're a minute over. Okay. I'll stop. Okay. Do you guys know what you need to do before Tuesday and going forward into Thursday? Okay, you're fine to sign off. I will stick around for some questions for a little bit. Not very long because it's my husband's birthday.
Thank you.
Okay.
Thank you.
I just have a quick question.
Yeah.
And then happy birthday to your husband. So just really quickly, we don't need predictor. We could calculate an ICC. We could get R to calculate an ICC from a data frame that doesn't even have predictors. All we need is.
You always calculate the ICC without predictors.
But I could just collect some. I could just collect some data on the outcomes and have a variable way to tell R what my class is.
You need to know who's in which class.
Right.
You can number them like class 1, class 2, class 3. You don't need to have Mr. Smith. You don't have to have identifiable labels, but you need to have unique, at least identification numbers to tell who's in which class. But yeah, you only need to know who's clustered how and the outcome in order to do an ICC.
Yeah, that's neat. Okay, thank you.
Yeah, so pilot data.
Yes, I'm on it.
Yeah. Okay. Joe, I got one computer. Are you got? Okay.